Hi everyone, this is a video to demonstrate some of the elements within TTPython, particularly for running across a set of devices that are not actually all together. So I'm going to be running a simple program. Let me show that to you really quickly. It'll be this program within an examples folder called Streaming Merge. So it's fairly simple. Basically, we're going to create two sinusoids. And we're going to add them together and also compute a moving average. So in essence, we have this, we have a root clock, we read from a clock, we set up some interval that it's going to sample for. It's going to be going for about 60 seconds. We'll make sure that the amplitude, phase, and frequency all show up to these sinusoid samplers so that it knows how long to produce this information. It'll be producing new tokens from these stream generators that have been streamified every 500,000 clock ticks, where the root clock nominally ticks at 1 tick per microsecond, so this is every 500 milliseconds. And the outputs of that will have a 100,000 tick interval width, which would equate to 100 milliseconds, so that whenever we have the two of these, we'll synchronize them for this addition, just a simple operation on two SQs, and then also show how a moving average can be computed on one of them. So basically this program has already been compiled. I can show that being compiled very quickly for you. I usually use this Jupyter notebook to do so. So here's the file. It'll know to look into the examples. So if I run this really quickly, it throws out a bunch of messages for us, but most notably we do see that there's this graph. It's not the prettiest of them, but we produce a bunch of constants. We read from a clock. There's sort of this setup, creating some TT times. I know this is very ugly. But we have these two sinusoid samplers. Those get merged together into one of the outputs, and this other sinusoid that's been sampled is turned into the moving average Y. So basically we're going to take this graph, distribute it onto three separate ensembles, one of which is my MacBook. That'll be used as the Runtime Manager, so it'll do some of like the network setup and teardown, as well as logging output tokens. We have another device. This is on the CMU campus. It's a LoRa gateway. Actually, it's a Raspberry Pi that's just running some of this code as well. It has a TikTok virtual environment, or rather just a virtual environment for Python that has all the dependencies set up. So this is the Raspberry Pi up here in the upper left. And up in the upper right is our LoRa CCSG server. It's an Ubuntu server that we use for testing some LoRaWAN capabilities. And each of these are going to be running as clients, this server and this Raspberry Pi, whereas my MacBook will be, it will be an ensemble itself, but it will have some special privileges because it is the Runtime Manager. So there are two separate programs that run. One of them is called Multi-Dev Test RTM. So this knows which programs to look for. If I could show that very quickly. It knows to pull a graph called Streaming Merge. It's a TikTok graph, a TT graph that's been turned into a pickle file, so it's been serialized just for storage. And basically, this thing is going to create the Runtime Manager. It knows to exist as a physical device, so it has an IP, it has a port. And basically, this is going to wait for some devices to connect, just a little bit of sleeping. It'll throw out an input saying that it's waiting for devices to connect. Basically, I will hit enter on my MacBook's terminal, after which it will try to instantiate and map the graph among the ensembles once they've connected. They were supposed to connect during this time. That's why I have the input there, so I can let them do so. After those devices have connected, we send in the input tokens, and then this is basically just going to run. The program is meant to run for about 60 seconds, so I have a timeout set of 60 seconds after it does that initial input sending. And then afterwards we're going to look at what the outputs actually look like. There's just some processing within this to pull token values and timestamps out of a log file and show them visually. So this is the Runtime Manager. It's sort of where more of the user interfacing is being done. There's also the client files, and those basically just connect to that Runtime Manager ensemble. They assume that they know the name of the Runtime Manager and the IP and the port, and actually show. So the Runtime Manager has two command line arguments. It's just the IP and the port that it's expecting to receive information on. I am using a private network through OpenVPN, so each of these can connect to each other directly. We do everything through UDP, so there's not any TCP sessions being set up or torn down, but they do need to have accessible network addresses for each other. So without further ado, I'll start with the Runtime Manager. So that's just going to be waiting here for a moment. And now it starts up the processes, and it is going to be waiting for devices to connect. So I'll start up these other two. And they have a little bit more information in their command line arguments, like this is the IP address of this Pi, and the port that it's receiving on. I generally use 8425, aka TIC, and 9-pad parlance. It also knows where it's expecting the Runtime Manager to be, which is 10.250.250.2. It's this device, as we just saw right up here. And the same thing is true for this other client ensemble. So I'm going to start that up. And those also have a similar, like, hit enter to start the test. So as I hit this, it'll join in here. So it tried to join the TikTok system, added itself to a routing table, and then this Runtime Manager also propagated that information back here. I'm going to do the same on this side. And we can see that actually as it propagated that routing table here, the same information of this new ensemble, the server, was sent to the Raspberry Pi as well. So there's sort of this this section where, as these devices are joining, the Runtime Manager needs to help everybody stay informed about which devices exist on the network. So now everything's setting up and it's waiting. These other two devices have a 90-second timeout, so I should go ahead and hit enter. So now I've just distributed the set of SQs onto the devices. We can kind of see which ones are here. Like there's a moving average, there's a sinusoid sampler on the server, there's an addition and a sinusoid sampler on the Raspberry Pi, and then there's some simpler stuff on the Runtime Manager, but they'll all be working together for this application. So as I hit enter, they're going to start spitting out values. So again, these two should be trying to sample this function, whatever it may be. It could actually be reading from a sensor, but right now it's just generating values for a sinusoid by maintaining a counter, and it's supposed to be running every 500 milliseconds. And so as they're doing that, they're producing these samples. One of these is computing moving average, one of these is adding the samples from the sinusoid together, and then this Runtime Manager, just the way that the random mapping kind of figured itself out, all it's going to be doing for most of this is logging some output tokens. Actually, this the Raspberry Pi timed out a little bit sooner than it probably should have, just because I was waiting as I was explaining some of this. So this was producing values during the meantime. They weren't really going anywhere. A lot of them were probably failing to be synchronized, particularly. Oh, actually that's not true. The add instruction was over on this side. So we only see part of this sinusoid. Generally there are about 3 peaks and troughs for this application if we had the whole 90 seconds, but unfortunately this one ended sooner, so we don't see all of that. We do see most of the sinusoid for the moving average though, since that was computed on this device, both the sinusoid samples and the moving average. So we show which SQ it came from and the ensemble it came from. There's all these timestamps down there. The weird format, that's just something that matplotlib does. It's not something that I have direct control over, at least in the general sense. Just to show this running one more time a little bit more smoothly, I'll start it up more quickly. So this is waiting for things to connect, connect, connect. Done waiting. Distribute the SQs. It's random, so there's no telling which ones will be placed on which devices a priori. I'm just going to go ahead and start out. I know that this has one sinusoid sampler and the moving average. This has the other sinusoid and the addition. So this is going to go and produce a sample, again, every 500 milliseconds for about the next 60 seconds based on that program that we originally wrote in TTPython, if I can find that again. Streaming merge. Right. And so you'll also notice that you can set the phase here. So the phase is set together whenever these timing intervals overlap. That's whenever we can synchronize them together for this addition. And generally with a width of like 100 milliseconds, that's plenty of time. There's going to be some variability with the way the operating system switches between processes on these different computers, and how long it takes for it to compute different parts of TTPython. But generally with like this interval width, I hardly ever see any issues. If I were to narrow that down to about 10 milliseconds, things would be different. So this was the addition. It was done on Ensemble 10, which I believe was, it would have been this ensemble, the LoRaC CSG server. So we produced all of these samples and we added them together. It was two sinusoids sampling one with an amplitude of 1, another with an amplitude of 2. So that worked out well, as did the moving average, which was being computed on this Raspberry Pi device. So that more or less concludes an example of TTPython running in practice. It's pretty easy to get this reproduced. In general, you would go to, I like to use the Jupyter Notebook because it shows the graph as its output a little bit more cleanly. So I usually compile a program within this interface. In doing so, it will produce a pickle file, which is just a serialized version of that program within the set of outputs. And then there are basically two files. One is the Runtime Manager. This is, I guess, more of a template for a Runtime Manager, where it creates its own ensemble, it waits for devices to connect, it takes the graph, it maps and instantiates the graph onto those set of ensembles, all of them, and then it sends out a set of input tokens to kick off execution of the graph. And then at the end, it processes some of the output tokens just so that we can sort of get a visualization of what happens. There's also an output log, which is actually where that information comes from. It's kind of big and nasty, and that's why I'm using some string processing on the side within that RTM multi-dev test RTM file. It's basically just looking at where the SQs came, or where the tokens came from, and the ensembles they came from, so that we can get a better idea of what the outputs look like. So the Runtime Manager kind of gets created first, waits for devices to connect, instantiates the graph and maps it, and then sends input tokens. And then the template for client devices is basically create the ensemble, do some of the normal ensemble setup, which is just like these 3 lines, and then connect to the TikTok network. One thing that users should probably be careful of is giving all of the devices the same address, where, well, the address is the IP and the port, but also the same name. So probably best on each device to have, say, a configuration file that you can read from, just so that it's a little bit more deterministic. In this scenario, the names are being generated randomly, which is, it can cause some errors in case some of the devices all name themselves the same thing and you have some address conflicts. But in general, this is a good template to follow whenever you're creating your own runtime system. Hopefully this video was helpful for you in figuring out how TTPython sort of works at runtime. There's a lot more information in the doc pages on some of the semantics of all of this. Please leave any comments on the video if you have questions.